without further ado, Bazat, the floor is yours.
Thank you very much. Before I start, I actually asked this question. I guess it would be more difficult to ask it in the virtual room, but maybe I can ask it here. How many of you have power systems background, and how many economic or background? Okay, and building engineering or civil? Okay, okay. So basically, based on this, that's what I was expecting. But I had already discussed with before what we will spend time on. Half of the slides we are going to talk about why does the thing we are doing here actually matter. That is, and then I will talk about what I'm doing, because if not, I will be just talking about something that you don't even see it useful. That's why actually we have planned it like so. We are talking about modeling thermal behavior in indoor environments, of course, in buildings, and then characterizing buildings or estimating the building characteristics. But first of all, why do we even care? That is the first question, please. So, of course, the share of the consumption of the buildings is around more than 25% of the global energy-related emissions and around 30% of the global final energy use. And the heating, ventilation, and air conditioning units constitute actually around 40% of that, which is really significant. And the problem is that it's getting worse, right? And because we are actually going to have some immigration toward more urban areas. At the same time, we also have, that's what we're going to discuss next, but we are going to have also an increase in the share of electricity demand within the full final energy use of buildings. And this is due to the increased use of air conditioners and, of course, electrification. So, these are the projections. So let's first look at it from a global level. So it's going to get. I'm using the energy outlook of 2019 because it's and the values are, as I said, the projections haven't changed much. But I believe that this representation was better for this purpose. We can see that the overall global energy consumption of buildings is supposed to increase substantially, specifically in developing countries. And so that is actually, if you want to divide it in different, let's say, countries or set of countries. And this is what we actually expect, because we are going to have an increase in the cooling ownership, substantial increase, specifically in China. We have a very significant increase in that. That's what we expect. Same in Australia, also in India. And also, apart from that, we are going to have more floor area per person. That's what we would expect. That, of course, it could be projected even much further. And that would also, of course, result in an increase in the consumption of buildings. But so this is, let's say, a global. Let me go back. Let's finish the global part. So basically, that's what we're going to observe here. So if we think about specifically developing countries, that means a lot of pressure on the local grid. So from power engineering part, that's what actually power engineers are going to actually deal with in the upcoming years. The same with energy planners, because either you need to empower completely the grid that needs a huge investment, or it will completely block the sustainable development of the country. Right? There's no other way. And that's actually what we are searching for, if we can find some sort of alternative, right? The specific case of Norway, of course, apart from the fact that it's a developed country, as a very, of course, you know better than me, main specification is that the heating sector is mainly electrified because of all this hydro, all historical reason. Electricity used to be very cheap in Norway, which that was also and also considering the capacity of the hydropower, it was a meaningful choice. And because of that, building sector already contributes to around 57% of the electricity used in Norway, out of that value, we have around 51% for space heating and around 9% for the domestic hot water generation. So putting everything together, 35% of the national electricity used in Norway is used only for heating, right? And so we saw it both in a global context and then the Norwegian context. But the problem is that usually we never hear about it. I think if you think about whatever you hear about on the news, political discussions, nobody talks about that, right? Everybody is talking about very specific green hydrogen to generate somewhere in the ocean and bring it back with some autonomous ships, right? But nobody talks about heating, and that is both in a European context and also, of course, in a global context, right? And the reason actually is that it's not good to talk about it first. Everybody thinks it's super optimized and there is no way, like we have already reached the saturation in terms of reaching emission. That is completely wrong. You've seen it in Italy, we have seen it in Norway. There is a significant room still to invest on this to make it. We still have very large electric boilers in Norway that could be replaced by heat pumps. Everybody knows that. And still, they are not given the priority they should be given, right? The same goes to, of course, the worst condition goes even to Italy. We have significant inefficiencies in terms of working, right? So this is in terms of the weight that the elephant has in the room. And apart from that, you have a second problem. And that second problem is that since we have these two cool ideas, that we want to add the electrical vehicles. For Italy, it's more a cool idea of the future. For Norway, it's more the cool idea that is already in place. And then you have to have PV generation in Italy is more common now. It's also, there are significant initiatives also in Norway to have more residential PV balance also to be installed. The problem is that the grid would tell you have a substantially variable generation, some consumption, you never know where it's going to start and where it's going to end. You never know where that, you can have a significant volatility in terms of consumption. And the grid can ask what this circus is, right? Because who is going to balance all of that, right? So apart from already we had already the previous problems that we had a volatility in the load and we had to balance that. We had already some wind generation here and there that we had to balance. But now we have also these little solar generation completely decentralized we need to balance. We have the EV and the electric vehicles we have to balance. And who is doing that? That is the problem. Either I have some stable generation, in Italy we have thermal power plants for that, which is a terrible choice. And we are talking about all of this for our sustainable development and a carbon-free future. And then we end up, to balance that, we end up using what we call the dirty thermal power plants, right? So that is the consequence, right? So and we knew already that on that grid, we have some fixed consumers, which are the buildings, we saw it's 35% only for heating in Norway. And how do we handle this? I actually added this. We're working on this national project in Italy. I've already discussed with the colleagues that are present here. They have warehouses that want to have PV panels on the whole ceiling. The warehouse we're working on is 50,000 square meters. And that is going to be equipped with electric trucks, right? And that's one warehouse, and that is located in a logistic hub in the north and near Emilia-Romagna. And there we have hundreds of warehouses. Imagine what is going to happen to the grid for that is not what is designed, it was designed for, right? So what is happening is actually we are discussing with several clients there. Everybody wants to do PV and electric vehicles. The problem is that they go to the utility or the DSO, and they easily get the no right over, right? There is no way they can do that, right? So that transition toward electric vehicles, like electrification of transport and decentralized renewable generation, is really blocked by that. At the same time, apart from the grid who is shocked by this issue, actually, we have the user. The user is usually happy to, if you talk with them about this, let's say, initiatives of sustainability, but the first time they want to pay for it, they are not that happy anymore, right? That's what is happening, right? You see it in all political movements. That's how you buy the vote. So that if you tell them that you're going to make them less bills, they will be happy. They would. Then, but at the same time, you need to show your society. There is a trade-off that it's never easy to solve, right? So what the user wants is that if I have a residential PV panel, I want to, let's say, self-consume it as much as possible. I want to maximize my self-consumption. I don't want. So imagine if I am generating power in the let's say around the lunchtime, and I'm not consuming anything at that time, and then I'm coming back from work and I'm connecting my electric vehicle. And then I'm consuming everything, like all other consumptions remain the same. I'm going to have a very low self-consumption. And then at the same time, I'm going to pay for the pick. In Norway, that there is a significant price for the pick, and the reason clear is that if I come back, I have all other appliances. I'm also connecting my vehicle. I'm going to have a very sharp pick that I have to pay for, and at the same time, usually that interval is the time the spot price is very high, right? So all of that should be handled anymore. The problem is, so imagine this is for a residential case. For the case of a warehouse, usually you have you charge your let's say material handling devices at night, and the PP is generating during the day, right? So either you buy like batteries larger than this room, which would cost you a fortune, or you don't have any, so you sell to the grid and buy it, and then you lose the whole economical let's say benefit, right? Because at least in Italy, the difference between the price you pay and the one you buy from these is really significant because of what it is. So both these residential, let's say, users and the commercial ones cannot have that, right? That's not supposed to happen. Because if we want to go forward with this, let's say, transition toward sustainability and having more decentralized generation and electric vehicles, we cannot have an elephant that is sitting. Because if he sits there and doesn't move, it means that we always have peaks, we'll always have a low consumption. So we need to move the elephant, right? At the end of that is our problem. So that's actually why do we need efficient buildings. That's the first choice. So first of all, I want to reduce as much as possible the consumption of the building. If you go to any, and that's usually what the reason why you don't hear much about it, if you go to any energy manager, facility manager of any building, they will tell you there is no room for improvement. That is the state of the art. And always there is, when you go to the mechanical room, you can see the rooms for improvement right in front of your eyes. But so first thing is to do that. And then once we have efficient buildings, we can make it flexible, right? That's IEA. Actually, there was a blog post about that. That actually represents well what I'm talking about, right? So we don't want. I'm not sure. Yeah, okay. So basically, we want to make it efficient, and then so I make my building efficient, and then I go and buy the solar panels, but I don't want it to be like that. Right? Because I don't want to pay for I don't want to sell and buy it again. So that's what I want, right? So I want it to become way more flexible, to have like some higher consumption here and lower consumption there, so that I can save, I can maximize what I'm doing here. I am paying less because I am maximizing the self-consumption, and I'm putting less pressure also on the grid, right? So we want buildings to be efficient and to have them to be also flexible. Actually, the reason why we are putting these terms like this is that, when we are talking about flexibility and then participation in flexibility market, for example, one approach would be like, if I have already a low base load, how can I become flexible? So it becomes like a cheating system, right? So you try not to show that you were non-efficient, and then you can show that you are flexible. That doesn't count, right? Of course, right? So that is actually why we always use these terms together, just to make sure no one is cheating here. And so this is, let's finish this verse. So we know that we have this problem, and it's a huge problem to solve. It's really strange, nobody talks about it. And you hear about it only in scientific conferences. When you go to the political discussions or news, that's that's something everyone is debating. But the question is, now I want to do something, I have some money, what to do, right? So what could be a roadmap? And so imagine if a municipality has a sort of investment, how can they decide where to invest? Right? That's because you can imagine the size and the number of buildings they have, right? So usually, for example, in Norway, because there is a regulation on that, the auditing is obligatory. You need always to have this auditing documents that are updated. Already, some, let's say, municipalities have problems with that because it's a really, let me go to the next slide. So building auditing. So I want to find out where these non-efficient buildings are to act on them. But the problem is that building auditing is a very slow and costly process. You need to go there, you need to do whole auditing procedures, preparing the report. That's why actually some municipalities have problems with that, because the rule actually imposes that you need to do auditing every 10 years, correct me if I'm wrong. And basically some buildings, they cannot even do that, right? And of course, in other countries, there is this regulation is something specific to Norway. There are plenty of countries that they don't have that regulation to be actually updating this audit, right? So we need something that is less costly and more scalable, right? And that's where we can have this smart, meter-driven remote auditing. So what I mean by that is that if you go and knock on people's house and want their mechanical room, that's usually something that's very hard to happen. It's more probable they would invite a stranger to dinner than letting them go and touch their boiler. That is what you can imagine. It's like that, right? So we need to have a non-intrusive methodology, and that's where what we call the smart meter-driven remote auditing, right? So what we want to do is to take only the smart meter data and guess what type of building it is, what is the performance class, and how it is operated, so that then I can go and tell them, look, you're consuming too much, so you should do this, right? I give you this money because I chose you because you're the worst one, right? So you need to find the worst, let's say, children in the school and invest on them to get them on board rather than. So that's the whole idea, right? And actually, this has been done. And Clayton Miller, that I've cited here, is actually a pioneer here. He had suggested a series of methods to do that, and the accuracy. And then we did some extension to that, some improvements. And I would say you are never going to have a 100% accuracy, but you would have a very, let's say, this is 70 to 80% classification. I'm talking about classification accuracy, just using the smart business data without any other input, right? So you just simply, what you do is that here you can train it with a set of buildings, you know their performance class and the use type and strategy, and then you train the model, and then you can guess it for new buildings, right? So it could be a very cheap method for a municipality, for example, to guess before doing the auditing, find the worst ones. Let's do auditing for that. I have just these 5 guys who are doing auditing in my office. I need to use their time. Let's find the worst ones and then do more investigation on that. The same, actually, since we are talking about the impact of heating, like let's say HVAC consumption in general, we have another method here that could be very useful, and that's using the smart meter data only and guessing what is the contribution of heating and because there I can actually do plenty of stuff, right? I can see what could be the possible potential in participating in demand side management. I can tell them how much they are paying. Actually, in Norway, many of these public buildings have separate smart meters for boiler and the rest, but there are plenty of buildings that don't have it, right? So that simply that awareness would help them, right? So you're paying this much, like X amount you're paying only for heating, act something on that, like do something for that. And then even you can guess if there is something wrong with their AC without even having seen it, right? So you can see if that is that consumption is higher, like if the variation with time, like if you have some historical data, you can see if that consumption with respect to temperature is increasing in an abnormal way. That shows that there is something wrong with, for example, the heat pump, right? You can guess it without even having seen it, right? And then you can also suggest them, look, you have this PV, you need to apply these modifications to maximize your self-consumption, right? That's actually why I am here, and that's what we are discussing with the colleagues here in NTNU and SINTEF. We are working on similar methods, how to disaggregate actually the heating consumption. That's the most important goal in Norwegian countries. So Sine is also, I guess, here, so she's also having all her PhD on this. So that is, let's say, but we are really enthusiastic. But so these are, let's say, till here we have had advertisement only, and let me see how much time.
More than 5 minutes.
Oh, okay. That's very short.
I want to extend the bit, and
maybe 5, maybe 10 minutes of initial. Yeah. So so this was advertisement, and now what we want to see is how these, let's say, machine learning-based pipelines can help us. And I've made a list of what could be the possible uses. I'm going to talk about this in this presentation, but the next ones I actually discussed about this before, right? So you can use these machine learning-based pipelines both for estimating how much would be the duration of flexibility in indoor environments. Italo, who is actually here, is working, he did his master's on that, and he's also working in PhD on that. But I wanted also to show, as much as we'll have time, on what could be, let's say, the pathway to develop these pipelines. So I would start with this morning ramp-up duration estimation. What do I mean by that? Is that when I'm talking about inefficiencies, that's the first point. If you think about it, imagine I'm talking about like a medical center in which we have these fan coils supplying the rooms. Usually how it is managed is that you turn on the system at a certain time, right? So it's the same also in Norway. You say like, turn on the whole room, all of the rooms at 4 o'clock in the morning, and then, or at 6, right? Who chooses that? One guy 15 years ago. But why don't they change it, or how do they know it's optimized? Nobody knows it's optimized, but nobody dares to change it. That's the reason, right? Because they will receive a call in the morning. So what they do is that they choose that time for the worst day of the year, right? But you can see, for example, that this room, it would take it 70 minutes. So what I mean by ramp up is the time it takes from existing temperature indoor to reach the set point, right? So here you can see it's already set. This is not going to happen in Norway because you have much more isolated buildings, but it can go up to that temperature in that building. How long does it take to bring it back to the set point we would like? You can see it's around 21.5, something like that, and 22 degrees, I guess. And this, you can see it's substantially different. In January, it takes 70 minutes. In March, it takes 15 minutes. So this choice of keeping it on, so what they do usually is that they choose the worst case scenario. The whole year they operated like that, right? Then it could be also two different rooms. The same day, one takes 55 minutes and the other 15, because one is small, the other one is larger, right? So now, how do I solve this problem? The problem is that the first thing that comes to my mind is to use conventional approach. That's what we used to do 20 years ago. Always, as you have a simulation software for each room, you build a physical model, and you design the windows in that model. You add all the characteristics of the walls, and then you guess. You can simulate how long it takes. That's a terrible idea, because you don't have the material characteristics. Nobody has that. It takes you 2 months to do that, and it's not even rapid enough to be used in real time, right? But why would we do that? Since already we have the data, right? So we know, we can measure the data. We have a BMS. We know how long it took in the last year, every day, every room, right? So what we can do actually, we can see it already here, how variable it is first, that it's changing substantially. This ramp-up duration is changing substantially by the indoor temperature, the starting indoor temperature, what temperature it was, and also with, you can see that for different rooms, it would have different behavior, but it's very variable, right, throughout the year. How do we do this? We train it with the historical data, right? So we see how it was actually behaving in the previous month, every room, every day. We can train it, and then we can guess it for the next, for the test set, right? So what is going to happen in the future? How do we do this? We can do it either offline. This means I teach for 6 months, and then I start doing the test. Or that's also a terrible idea. The reason why this is a terrible idea is that things change. So your fan coil can get a fouling, something can move, and you might put like a large computer in this room. So something change by time, right? So what you can do, you can use this sliding window-based training. So you train based on the last 20 or 10 days, and that's enough, right? So you just say, what happened in the last 20 days? I can train with that and then use it to predict the future, right? And 45. Yes. I just have one conclusion. I finished because okay. And basically, so based on this, what are the inputs of that model? you would choose them. That's why I have added them as physics-based, let's say, features as the title of the presentation, because let's say, instead of using a physical model, what you can add is your physical idea of the problem, right? So if the person doesn't have any idea about how buildings or indoor environments work, they would put just the temperature right now, right? But we know that you could consider also like the slopes of temperature in the previous X minutes, right? And also the external conditions with lags, because there is a significant lag in the walls, right? Actually, I wanted to show you the results here. That's, I think, something interesting. So if we did this feature set, I don't want to go into it, it would take me 3 hours to talk about it. But we did this feature selection, and we saw that the outdoor temperature is not even chosen. Why? Because the slope of the indoor temperature 30 minutes ago and now actually represents it, right? So why would this method be useful? Because if you do it for you are working on several other applications, I can understand. Once you do that feature selection, you can remove a sensor, right? That's a substantial cost reduction, right? So these types of, let's say, methodology gives you also an edge on that. Plenty of other stuff, but I think we should start the discussion.
Thank you very much.